deal? Sick. Okay. So question 1. You want to investigate the impact of nitrogen deposition on plant species composition at the dunes. You set up 30 plots in similar plant communities at the dunes. You assign 15 plots to the nitrogen addition treatment. You add nitrogen fertilizer to those plots. And then, you're going to compare the ones that you added the extra nitrogen to the ones that you did not add the extra nitrogen to. So whenever you're doing something like this, I suggest you just draw the figure out. And you're like, okay, well, what do I have? I've got, what's my independent variable here? Who can tell me?
Nitrogen deposition?
It's nitrogen. Yep, nitrogen deposition. So check it out. Think about it this way. Always think about it as my dependent variable depends on the independent. So what I'm saying is that species composition depends on nitrogen deposition, not that nitrogen deposition depends on species composition. And if you make yourself state it that way, you'll have a way easier time of always telling apart the independent and the dependent variables. Cool? So now, on our x-axis where the independent variable goes, we put nitrogen deposition. Okay? There were 30 plots total. Half of them had nitrogen fertilizer added to them, and the other ones didn't. So we've got added fertilizer and no added fertilizer. And what are we going to be measuring? We're going to be measuring plant species composition, which is a little vague, but I'm just going to put plant species composition, PSC. It's probably going to be a Shannon diversity index. So what's our figure going to look like? Something like this, probably. All right, cool. And now we've got a rough, fake figure that we can work with. So, what's the null hypothesis of this study?
Addition of nitrogen fertilizer has no impact.
Exactly. Remember, H sub O is always independent variable, has no impact on dependent variable. And life gets way easier if you sketch out your figure like this. So let's go with the addition of nitrogen fertilizer has no impact on plant species composition at land period. That's your null hypothesis. Question 2. In the deposition of what type of test do I use? What type of test do I use when a figure looks like this? Same answer? Yeah, same. Solid. T-tests. Yeah. 2 categories and then a continuous dependent, right? T-test. In the nitrogen deposition experiment described in the first question, analyze your data, you get p-value of 0.51. So let's change our data a little bit. Say it looks like this. Boom, boom. I want it to look like this. That's perfect. I wouldn't say perfect, but it's good enough. All right, p equals 0.51. All right. So, look at the error bars, they don't really overlap. So, maybe there's a difference. Well, what does that p-value tell us?
Species composition is not affected by composition.
Yeah, that's correct. That's what everybody said there, right? It sounded like that? 6. Species composition is not affected by nitrogen deposition at Landfield. And now you're a fisheries biologist. Congratulations. Okay? And you're interested in understanding the relationship between distance upstream from the ocean and density of juvenile salmonids in the Klamath River. So I don't know if you did a lot of word problems. Back when in Washington they had this thing called the WASL. It was a standardized test. And they taught us to just see text like that and just disregard it. I was like, that doesn't matter. This is a stats question. You do snort, it doesn't matter. Here's what matters. 1 mile, 2 miles, 3 miles, 5 miles, 10 miles, boom, boom, boom. You're going and surveying at all these different distances. to investigate the relationship between distance from the ocean and salmonid density. All right? So if I'm going distance from ocean here and salmonid density over here, and I've got all of these different points where I'm measuring the data, right? And then I'm measuring like here and here, and getting these values and these values and this value and then this value. Let's screw these people up. They don't get bad data. It's not bad. But anyway. So what statistical test would be good for that?
T-test? Or no, not T, linear regression.
A linear regression. Now, we're always going to be using linear regressions, but sometimes it would be better not to be using a linear regression. Like, let's say the data went like this. Okay? You're not really going to do a linear regression on that. But like I said before, that's the sort of stuff, those different models, those different lines, those different regressions, those are going to be the things that you'll get in your future ecology statistics work. And this work gets interesting. Yes?
Could you also use the chi-square for this?
You can usually find a way to use the chi-square for most tests if you're like, okay, well, I'm going to propose that the density of juvenile salmonids will be a number, but you have to have a number, an expected value. And here, with the regression, you don't have to have an expected value. All you have to say is, oh, distance will have some impact on density. So you see why it's, depending on the background data that you have, this is easier. But if you wanted to say, okay, well, in the next year, I want to see if the salmonid density has changed 50 miles away, you could compare your expected values were last year's and your observed values are this year's, and you can compare that way with a chi-square. But that's also, there's no reason not to just run that as a t-test. Yeah. So it's rare to find a good chi-square application, but they do exist. Okay. In the hypothetical salmonid study, salmonid, right? Salmonid. Yeah. That's what, yeah, right?
Yeah.
Okay, cool. Salmonid.
Whatever you say.
The more you say it, the worse it sounds, you know? Like, again, that sounds silly. Okay, in the hypothetical homogeneous study, described in the previous question, what's the null hypothesis?
There's not a linear relationship.
Yeah. There's these proposed, like, oh, there's going to be more, there's going to be less. There's not a linear relationship between distance from the ocean, and yep, this is different than there's no difference in the number at the mouth compared to the headwaters, because that would be a t-test, all right, comparing like this data to this data. Now, could you do that analysis in addition if you have this data set? 100%. Why not? Question 6. Now you're a wildlife biologist. Congratulations. Okay. Does antler size affect reproductive success in Roosevelt elk males? Okay. You count the number of points on each antler, and you track whether the elk is successful in mating with a female elk in the herd. You divide the elk into 2 groups based on the number of points. Group 1 includes elk with 2 or fewer points. Group 2 includes elk with 3 or more points. So, you know, number points, you have, less than 3?
2 or less, 3
Thank
or
you.
more.
Less than or equal to 2, and then greater than or equal to 3. And you just have each one of those categories. So probably, as I'm writing this out, it's coming together like, oh, well, yeah, my data is probably going to look like this, and I can just fit a bar to that. My data is actually going to look like this. Fit a bar to that. Third test.
So, this is assuming that, like, within the group you're counting, it says you track whether or not, whether or not the specific elk was successful in mating, is that not categorical?
Great.
Is
Yeah,
that-
yeah.
like you
So
said?
whether or not each one is successful, yeah, that is actually a really good example of categorical data. Okay, solid. So what we would be looking at here is proportion of the elk that mated, right? If we look at my PowerPoint, this is going to tell us that this is when we could actually do a chi-square, if I'm not mistaken. Categorical chi-square, flawless. All right. So this is when you could run a chi-square test. The issue is 100% like figuring out what your expected value would be. That's the biggest issue right here, okay? It's like, you're going to find out if each one made it or not. That's a binary piece of data. And then you're going to probably end up transforming that into the proportion of individuals that mated, okay? And then you would need to figure out an expected value for that, all right? A chi-square, I think that's always the tricky part. So, yes, based on that, you could do this as a chi-square test. But I will tell you that also you could do this as a t-test if you took those categories of mated or not mated and you converted it into proportion of individuals that mated. Alright? You just need to do multiple days of observations. Like each day, the proportion of elk that mated, you know, you'd be like, oh, 0.01, and then 0.4. Then you can take the average and do it as a t-test. So I would accept chi-square test here 100%, because that's what the table tells us, and a chi-square test would be, you know, would work. I would also accept t-test, so I'm gonna need to change probably a setting to make sure that I've got this one set up to accept both of those as correct answers. Oh, you know what I'll do is I'll just add another option that says chi-square or t-test, depending on how you process the data. But I'm gonna put chi-square right now, and we'll see how that goes. In the Roosevelt Elk study above, okay, let's say you divide the elk into 4 groups based on the number of points on each antler, okay? Group 1 is 2 or fewer, group 2 is 3 to 4, group 3 is 5 to 6, group 4 is 7 or more, okay? So, technically, once again, it's categorical versus categorical. And you could run another chi-square test, but with more degrees of freedom. But in most instances, alright, you would run this as an ANOVA, okay? You would get the data about what is the proportion of the offspring that made it. So I'm gonna, cause I wanna get 100% on this, I'm gonna put t-test and ANOVA, because I bet you that's what I wrote. Alright, cool. Don't worry, just don't submit. I'll make sure I change the settings before anybody submits their thing. Okay, a low R-squared value in a regression analysis. Okay, cool. So remember, R-squared value has to do with how closely the points adhere to the line. Alright? So this right here is a high R-squared. And in this graph right here, this is a low R-squared value. Okay? So, remember that the R-squared value is not the same as a p-value. Okay? So let's take a look at these answers. The relationship is not significant. Well, that's our null hypothesis. And the R-squared value doesn't tell us It's not a p-value, so it doesn't tell us about that. The model does not fit the data very well, or the model fits the data, or the relationship is significant. So these are eliminated. These can't both be true. So a low R squared value, right here, the model, which is y equals mx plus b in this case, okay, the model does not fit the data very well. Okay? Solid? Cool. So don't submit yet, because I gotta double check those dang answers about the chi-square. Let's see. Oh yeah, so I put them as t-tests and ANOVAs in the answer key, right there. Very good stuff. But you're 100% right, that those could be run as chi-square analyses. Alright. The trick would be figuring out